This car just got hit by a 7.62 millimeter rifle round, the kind of bullet that tears through engine blocks, the kind that punches clean through brick walls. And this vehicle didn't flinch. But here's what nobody tells you. It's not the steel that makes it bulletproof. It's not the glass. It's not even the thickness of the armor. It's the precision of every single step in a manufacturing process so complex that most factories in the world can't even attempt it. Today, we go inside the factory, from raw steel coils to a fully armored police vehicle that can survive what most cars can't even imagine. Let's build it. Most people see a police vehicle on the street and think, that's just a regular car with flashing lights on top. They couldn't be more wrong. The global police vehicle manufacturing industry is worth tens of billions of dollars. And every single year, thousands of these machines roll off factory floors, with price tags ranging from $100,000 all the way past $500,000 per unit. But the price isn't what makes them special. Think about this. A fully armored police vehicle can weigh 70% more than a standard car. 70%. That's like attaching a second car to the bottom of your vehicle and still expecting it to corner at speed, stop on a dime, and survive a high-speed pursuit. How does it hold together under that kind of stress? That question has one answer: manufacturing precision. Let's start at the very beginning, the raw material. It starts here, giant steel coils, each one weighing several tons. But not just any steel. Police vehicles use high-strength armored steel, a material with dramatically higher tensile strength and hardness than the steel in your everyday car. Standard automotive steel bends under pressure. This steel doesn't. Overhead cranes carry these massive coils to an automatic uncoiling system. The steel rolls out slowly, passing through guide rollers that keep it perfectly straight. And here's where the quality obsession begins. Cameras and sensors scan every inch of that steel surface, looking for cracks, warping, microfractures. Any defect, no matter how small, gets flagged immediately. That section is cut away and removed. No compromises. The steel is then flattened by rolling and pressing systems, cut into standard sheets and stacked, ready for the next phase. Because what happens next is where flat metal starts becoming something extraordinary. Inside the CNC processing area, the air smells like heat and metal. High-power laser cutting machines go to work, slicing out components for floors, walls, doors, and pillars with a precision that human hands could never match. These aren't just flat plates, they're structural components, each one engineered to a millimeter-level spec. From cutting, the pieces move to hydraulic stamping presses that apply hundreds of tons of force. Flat steel transforms, curving, angling, bending into complex three-dimensional shapes. And those angles? They're not just for looks. Every curve is calculated to deflect impact forces. When a projectile hits, the geometry distributes the energy, instead of concentrating it in one point of failure. After stamping, CNC drills create bolt holes and connection points with the kind of accuracy that only computers can guarantee. At this stage, every steel piece has its final shape, but shaping the components is only half the story. Now they need to be joined. Welcome to the automated welding line, where robots do in seconds what would take a human welder hours. Pre-programmed robotic arms position each component with sub-millimeter accuracy. The welding sequence is calculated in advance because order matters here. Heat causes metal to shrink, weld in the wrong order, and the entire body warps slightly, invisibly but dangerously. The robots control heat input precisely, preventing deformation at every step. Floor panels, sidewalls, roof frames, all join together into a complete body structure that is simultaneously rigid enough to stop a bullet and flexible enough to absorb a crash. But how do you know it's right? How do you verify that every weld held, that nothing is off by even half a millimeter? You scan it. After welding, the body enters the geometry inspection area. Laser scanning systems map thousands of points across the entire vehicle structure, building a precise 3D digital model in real time. This model is then compared against the original design files. Every deviation is flagged, every misalignment identified, down to the exact location and size of the error. If a dimension is wrong, the system stops everything. The problem gets fixed before it goes any further. Because a vehicle that passes visual inspection but fails at the molecular level, that's the vehicle that fails on the street when it matters most. Only when the body passes this invisible examination does it move to the next phase, protection from a different kind of enemy, corrosion. The vehicle body passes through a multi-step cleaning system, every trace of oil, dust, and impurity removed. Then it's submerged in an electrophoretic coating bath. Electric current pulls paint particles into every gap, every seam, every hidden surface, places a spray gun could never reach. This first layer of protection guards against rust from moisture and chemicals. Critical, because once the armor goes in, many of these areas become permanently sealed, untreatable forever. The body then moves through high-temperature ovens, curing the coating into a hard, durable bond. After that comes the finish paint, robots and workers spraying precise, even coats under strict thickness control. Every surface inspected under high-intensity lighting. Meanwhile, on a parallel track, the gasoline engine gets lifted by crane into the frame. Transmission connected, drive shaft installed, fuel lines routed and inspected. The mechanical heart of the vehicle is beating. Now it's time for the most critical phase, body meets chassis. This is the moment the vehicle becomes real. Robotic systems lift the completed body, holding it perfectly stable in the air while the chassis is positioned underneath. The descent is slow. Every connection point must align precisely. 1 millimeter off, the system stops. Operators investigate. They fix it. Then they try again. When alignment is confirmed, automated tools tighten load-bearing bolts with computer-controlled torque. Mechanical, electrical, and fuel connections are completed. 2 separate systems become one unified machine. And now, the second shell goes on. Steel armor plates, processed from the same high-strength steel, CNC cut, stamped, and bent, are positioned inside the body cavity. Workers secure each plate to the frame using welding or high-strength bolts. Tightly integrated, no gaps, no weak points. This isn't a shell around the vehicle. This is a second skeleton inside it, designed to absorb and disperse impact forces so the cabin stays intact. While the body is being assembled, the bulletproof glass is being built in a parallel process. Multiple layers of glass and polymer, stacked alternately, pressed together under high temperature and pressure until they fuse into a single unified structure. When a projectile hits this glass, the outer layer may crack, but the inner layers hold. No shattering, no fragments entering the cabin. The glass is installed into reinforced door frames using specialized adhesives because standard door hardware can't handle the weight of bulletproof glass. Inside the cabin, wiring harnesses are routed throughout, connected to dashboards, screens, control systems. Seats are bolted to reinforced floor mounts. A security partition goes up behind the driver, separating the front from the detainee compartment. Communication radios, electronic sirens, signal light controllers, cameras, recording systems. Everything a law enforcement vehicle needs to operate in the most dangerous conditions. The final stage, exterior assembly. Wheels mounted and torqued to specification. Front and rear lighting units installed. LED light bars, sirens, police markings, mounted, wired, tested. Mirrors, door handles, trim panels, every external component inspected for durability. Then, the vehicle hits the test track. Every system is pushed to its limits: brakes, suspension, engine performance, communication systems, electrical systems, sealing against water and dust. And the armor? Tested against the threats it was built to face. Only when every single checkpoint passes does this vehicle earn the right to carry the officers who protect our streets. From a raw coil of steel to a machine that stops bullets, this is what precision manufacturing looks like. This is what engineering obsession produces. And this is what stands between officers and the threats they face every single day. If you found this fascinating, you know what to do. Hit subscribe, because next week we go inside the factory that builds military helicopters. See you there.